kind of keep a record of it. Okay, so this will be a review of acid base equilibrium. All right, first thing you want to remember is what constitutes an acid or a base or something of that nature. So we want to talk briefly, before we jump into the exam, the character of acids and bases. Okay, and I gave an acronym, don't remember when, but if you'll use GRIT, grit, it will be real easy to remember just the primary points of acid-base characteristics. They're galvanic, they react to yield a salt plus a weak electrolyte, which for the most part is water typically. They're indicator sensitive. And taste, bases is bitter, and an acid sour. Now, one of the things that I want you to remember on the indicators is litmus. Red litmus goes to blue when you're using a base, when you're testing a base, and blue litmus goes red if you're testing an acid. So while that's simple, it's very important that you remember these characteristics and certainly stay in the middle of them. Okay, that's one issue. Another issue is why is an acid and a base a base? What is it about HCl is HCl? I mean, what's the big deal? Okay, acids and bases, regardless strong or weak, are electrolytes. And the word electrolyte refers to conduction of electricity in aqueous solutions. So the first thing is acids and bases require water, and then they require ionization, and then as an electrolyte they conduct electric charge. So some reactions will give a byproduct of, say, a strong acid, HCl or hydrogen bromide or something of that nature, and it'll come off in a gas phase. Well, that's not an acid in the context of what we're talking about. An acid is an acid because it's in water and ionizes and will conduct electric charge as an electrolyte. So that's another point that I want you all to kind of keep in the back of your mind as you will see questions on that idea. Okay, now strong and weak electrolytes in terms of acids and bases, it's very important that you have these down in terms of, well, what are they? Okay. Well, they're electrolytes, and by definition, an electrolyte that ionizes 100% is called a strong electrolyte, and then a weak electrolyte doesn't ionize 100%. So we want to review the strong acids. Okay, so in the strong acid world, The strong acids are listed here, and I think we beat it up enough. What's a weak acid? Anything that's not a member of this collection. Anything not a member of the strong six. In some published literatures, you will find more than 6 acids listed as strong acids, things that have a high degree of ionization. H2SO3, sulfurous acid, is frequently listed. Now, I was taught that if an acid has a Ka value, regardless, it was a weak acid. These are the only acids and that I know of, 45 years of playing with chemistry, that will not have a Ka value, or their Ka value is infinite. Okay, so if you can look up a Ka value for an acid that's published, my definition, and somebody will argue with you, and it never fails, my definition is that that's a weak acid. It has a Ka value. Okay, so I just wanted to throw in that little note. Strong bases, let's look at that real quick. Strong bases revolve around Arrhenius bases, not the Bronsted or Lewis bases. Arrhenius bases are known to deliver hydroxides, OHs, into solutions. That would constitute the Arrhenius type base. The strong bases are group 1A and group 2A hydroxides, except beryllium hydroxide is not functioning 100% ionized. So you want to certainly be aware of these and be able to, when you see them, and if they're asking you the pH of a 0.1 molar sodium hydroxide, you know you're going to get 0.1 molar in hydroxides, and then you take the apply the proper equations. Weak bases are ammonia and ammonia derivatives. These have another name called amines. Ammonia is NH3 with a pair of electrons on it, has a pyramidal geometry, looks like that, and so forth. In water, the electron pair will coordinate covalent bond to one of the hydrogens, and you'll have NH, an extra 4, 4 hydrogens, and not 3 anymore, one it moves up, and then hydroxide. It is this that ionizes as a weak electrolyte, right there. If you have an amine, just to review this, you pull off one of the hydrogens and put a substituent group on there, something that's real weird. That is, we call it an R group, NH, and see I pulled off one of the hydrogens. Well, in water, you just increase your hydrogens by 1 and hang the OH on the end, and there's your weak electrolyte. Right, so the R value can be any kind of weird structure, ring structure, like that, and you put it in water, it'll go to this. That's aniline and anilinium hydroxide. And then you would figure your weak electrolyte and weak base problem on this, and it'll have a Kb to equal, I don't know, something. it'll have a number, and that'll be given in the problem. So it's one of those OH is equal square root formulas, and Kb times the concentration, and same way with the weak bases. Okay, analytical chemistry of acids and bases always begins with the autoionization of water. Okay, so first topic that you need to keep in mind is autoionization of water. Here, HOH equilibrium goes to H plus plus OH minus. And to repeat this very quickly, at equilibrium, we disregard the water concentration or the amount of water because it's infinitely larger than the ions that are delivered. That is 10 to the minus 7 molar in hydrogen and 10 to the minus 7 molar in hydroxide, and that's in a pure solution at 25 degrees. See, not pure solution, pure condensed phase water. So it turns out that this will give you what is known as the ionization product constant for water, Kw value, and establishes the foundation of what we call the acids. What's acids or bases? If the hydronium ion concentration is greater than the hydroxide ion concentration, then of course it's an acid. Hydronium ion concentration equals the hydroxide ion concentration, and that would be, this case, in pure water, is neutral. And of course, base would be greater if the hydroxide was in a larger concentration. Okay. Now, in the application of this, you can go straight to this if you are working with strong acids and strong bases. So use Kw direct, if you understand what I'm saying, direct if using strong acids and bases. So 0.1 molar HCl, for example, you can figure what the hydroxide concentration is by plugging in the 0.1 for acid, because it's going to ionize 100%. And then you divide 0.1 into 10 to the minus 14, and you get the hydroxide concentration. Now that's direct for strong acids. Also works for strong bases because they ionize 100%. In weak acids and bases, okay, you have to apply the square root formula. Now we're talking about a weak acid or weak base only, not the common ion effect. For weak acids, typically your hydronium ion concentration is the Ka value times the acid concentration. Okay, once you get that, then you go to the Kw and apply it as needed, because you have, if they're asking for a POH, then you'll have to calculate this, and then what you get, put it into the formula. I can write it down, right? Okay, everybody on that? Now you got to be able to recognize weak acids and strong acids, and then make a decision on how to solve the problem. And of course, for weak bases, don't forget the hydroxide is equal to Kb times whatever the weak base concentration is. Then, if the problem were required, then you go to the Kw expression. But in weak acids and bases, you have to put in those square root formulas to get to the Kw expression. But in the strong ones, you can go straight there and then make your identify. Okay, ionization in polyprotic acids. What's polyprotic acid? Well, it's an acid which has two ionizable hydrogens. Example would be carbonic acid. H2, H2CO3 has two ionization steps. H2CO3 delivers the first concentration of hydronium ion, and you'll have a CO3 bicarbonate ion left hanging on the end. Then that's the first ionization. Second ionization step would be the bicarbonate ionization to give another hydrogen plus CO3 2 minus. In this world of diprotics and polyprotics, you have an ionization constant for each one. Okay. The ionization product in these always, Ka1 will be significantly greater than Ka2, which means the second hydrogen is more difficult to pull off. And so to illustrate this, here's the structural formula for carbonic acid, and when it ionizes and delivers the first ion, here is the bicarbonate. Sorry, I'll do it this way. And so that's carrying a negative charge overall. Well, that negative charge functions to hold that second hydrogen on much, much tighter. And it's harder to ionize the second ionization step than the first, and that's why you have a lower Ka2 value. A couple of factoids in here. For most problems, I don't have any problems on this exam that doesn't follow this prescription. Assume all hydronium ions come from the first ionization step. If you're left to right in calculating ionization, that is, when I say left to right, you start with H2CO3, make the first ionization, H bicarb, second ionization. Now there's a problem on the test I saw where they are asking you for the acid pH of a sodium carbonate, and the carbonate is the first ionization in that. So you get all your ions from the first ionization. Now we'll get to the carbonate, so it'll be a little bit backwards. We'll show you that in a minute. To understand the idea of hydrolysis, about the definition, let's start there. Hydrolysis is the reaction of salt ion with water. And if it does react, it may or may not change it will change the equivalence point, pH. And we have really four cases, but we're only going to worry about three. Salts come from acid-base reactions. So if that's the case, then we have four kinds of acid-base reactions we have to take into account: strong acid, strong base, or a weak acid reacting with a strong base. 3, strong acid reacting with a weak base. And 4, both of them weak acid reacting with weak base. Okay? They all produce salts that may or may not affect the pH at the equivalence point. If you have a strong base, it produces a salt. No reaction or no hydrolysis occurs. Because if you tested the salt ions from a strong reaction and moved the hydrogens, hydroxides to the ions, they would all be strong acids or strong bases. And if you get a strong acid or a strong base after you test the reaction of the ions with water, your conclusion is no reaction. But if you have a weak acid or
reacting with a weak base, it will give you a salt whose anion will react with water, forming a weak acid and an excess of hydroxide. So this gives you a pH greater than 7 at equivalence point. We'll work a problem or two as we go through this. I'll try to find some exact issues. This one will produce a salt whose cation reacts with, I better put that up here top, anion reacts with water and results in an excess of OHs. Here, pH at equivalence point is less than 7 because cation reacts with water. Okay?
So if the cation reacts with water, the positive is going to pull the OH over and leave an excess of hydronium ions.
Okay? Weak acids will produce a salt stronger, or the larger Kb value, or larger K value will dominate.
So we're not going to have that. You won't have to worry about that one. Try to figure out who's delivering the most acid or most base and this kind of thing. Now, in solving problems dealing with this, you have to work with the hydrolysis reaction that actually occurs. I want to emphasize this. Say we have a weak acid, say HOAC, reacting with a strong base, NaOH. Make it look like an NaOH, and so we have an NaOAC generated plus H2O. So that's your first reaction that you need to deal with in a hydrolysis problem. The second reaction is ionization of the salt, and so as NaOAC goes to Na plus OAC minus. And this pattern is the same for the weak base, strong acid. And then you test each one reaction with water. Na plus HOH gives NaOH plus an excess of hydrogen, if it occurred. However, because that's a strong base, you don't have that reaction. So that conclusion here is no reaction. The acetate anion will react with water and set up an equilibrium of a weak acid plus an excess of hydroxides, and that's what accounts for the shift in pH, the increase in pH at the equivalence point. So if we assume initially change in concentration at equilibrium, say we had a 0.10 molar salt that was formed, then this is going to, before it reacts with water, you don't have any products. This will go down by X, up by X, up by X, X, and 0.10 minus X, and you can drop the X 0.10 molar. Okay, next step down here is to write your equilibrium expression for the hydrolysis equation. You will not include the water in your hydrolysis equation. Now, one thing you need to note here, OAC is minus, it's a conjugate base. So you're looking for a Kb prime, as I indicate. Now this is, of course, for the OAC minus. Well, since it's not published, we have to use Ka times Kb equal Kw and solve for Kb to get that. So there's your K value for the hydrolysis reaction right here. So you want to set up your products over reactants against this right here, and then substitute your equilibrium row, solve for X, and you get your OH like that. So we'll see, here's your products. Divided by, well, your salt, OAC minus.
And then if we put the equilibrium row in, we have x squared over 0.10. Solving for x, which is the hydroxide, and that would be, I didn't do the, okay, that'd be 1 times 10 to the minus 14 over the Ka. For acetic acid, I'm going to simplify it, just say it's 1 times 10 to the minus 5.
And it's actually 1.8 times 10 to the minus 5, but
You get my drift here. And so that is 10 to the minus 9 when you calculate it. So we're solving for x, so that's 0.10 times 10 to the minus 9 square root moles per liter. So that's 9 and 1's 10, so that's square root of 10 to the minus 10, or 10 to the minus 5 mole per liter in hydroxides. Okay. Now, you can calculate your acid concentration using the Kw expression, or you can take your POH and apply it to pH. We'll do it both ways. Okay, if this is your hydroxide concentration, 10 to the minus 5 molar, then you can get the hydronium ion concentration to equal 10 to the minus 14 over 10 to the minus 5, and that'll give you 10 to the minus 9th molar in hydroxide. Hydronium, sorry, molar. And pH, as you know, is minus log of the hydronium ion concentration, which equals minus log of 10 to the minus 9, which is 9, or basic, which is you expect in that case. Or take your given your hydroxide, you can get your POH to equal minus log of the hydroxide concentration, which is equal to minus log of 10 to the minus 5, which equals 5. And the pH is equal to 14 minus POH, which is equal to 14 minus 5, where it's 9 again. So either method will serve you well and give you the answer. Now, I present all of this in that order, so you'll have a complete little mini package of how hydrolysis is solved. And you have a couple of 3 problems on that on the exam. We had one on the quiz today on common ion effect. Common ion effect is one of the ions of the acid or base undergoing dissolution, or salt undergoing dissolution in whatever you're working with. Okay, I think I've beat you all to death enough with the definition and function of the common ion, but you should expect a comparative in terms of problems on there. Which of the following would reduce the pH the most, this kind of thing, and that'll give you some salts that are possibilities. Anyway, to make that comparison, you need to be able to calculate first the ionization in pure water, given 0.10 molar HOAC and 0.01 molar, say, sodium acetate, like that. And so you get that problem. Okay, how does the pH change? Or if we're working with a salt, another one would given, say, given silver chloride, you don't have a concentration is saturated or not. Silver chloride in 0.001 molar, I don't know, HCl, like that. And then you'll compare solubilities. And we'll give you the Ka values for this one. Ka is equal to 1.8 times 10 to the minus 5. And this one will be KSP, which equals 1.8, correct? 0.8 times 10 to the minus 10. And so you
now are able to compare extensive reactions between acids and bases and or salts and so forth. So take that first one right there. In pure water, HOAC minus like that, and you can use the square root formula to get your hydrogen ion concentration. Ka times the acid concentration, and so that's the square root of, well, I'm shortening this up. I'm going to say it's 1 times 10 to the minus 5, okay? So I got 10 to the minus 5 times, say, a 0.1, 10 to the minus 1, and so that molar, which is 10 to the minus 3 molar in that pure water issue. Now, there are two problems that you can expect in this. One, percent ionization, and B, pH of the system. So you got two kinds of problems that'll pop up at you. If you're looking for percent ionization, it's whatever your hydrogen is over the acid concentration you started with times 100%. And this one, 10 to the minus 3 over 10 to the minus 1 times 100%, and 1.0% in that one. Okay, so that's one possibility. Or if you had a pH, which is minus log of hydrogen, minus log of 10 to the minus 3, of course that's a 3. So expect that, okay? Just trying to give you a cross-section of everything that you're going to see on Thursday, okay? And you be ready for it. This one really looks to, you can calculate a pH of a salt, okay, in this context. The solubility of this is a 1-to-1, so for AgCl and KSP equals 10 to the minus 10, 1-to-1 ionization solubility is square root of KSP, square root of 10 to the minus 10, which is 10 to the minus 5 molar. Now, if you throw in a common ion in that, 0.001, you have to use the equilibrium expression. Okay. We've got it in the presence of HCl, 0.001 molar there. And so you're looking for X to define your solubility. So KSP is equal to silver chloride, which is X, times 10 to the minus 3, which is 10 to the minus 10. So your solubility, 10 to the minus 10, 10 to the minus 3, 10 to the minus 7 molar. And you'd compare the two, and certainly the pure water is more soluble than the common ion presence, okay? So, okay, buffer systems function to reduce the changes in pH when acid and base are added to the solution. So that is the primary. The composition of a buffer is the weak electrolyte and the salt of the weak electrolyte. Because of the salt presence with the weak acid or weak base, the overall function is based upon the common ion effect. So the overall, or the chemical function of a buffer is based
uncommon ion effect. So if you want to solve problems and with buffer solutions and so forth, you solve them as though they were common ion problems. All right. So if we had a HOAC, let me give you some numbers: 0.10 molar HOAC. I'm picking easy numbers to get through this, and 0.10 molar sodium acetate. Now, sodium is only a spectator ion, so it doesn't enter into the calculations at all. So, but you can't throw in an acetate ion without having some counter ions. But anyway, this is referred to as a 50-50 buffer. When the salt and the concentration of acid are equal, when you mix your buffer, we call it a 50-50 buffer. And this is the most stable, most practical that you would use. If you want a different pH than what this would generate, you would have different amounts of salt and acid, and you have to calculate that using the Henderson-Hasselbalch equation. I'll show you. Okay, for a buffer problem like this, we find that if for a 50-50 buffer, the salt concentration and the acid concentration will cancel out of the Ka expression. Here at equilibrium, 0.10 molar, 0.10 molar, and there's your hydronium ion concentration. Make it look like an X right there. Well, Ka equals acid, OAC, those are molars, concentration. And if those are equal, then you have nothing but 0.10 divided by 0.10 molar. Those cancel out. And so at a 50-50 buffer, your Ka equals your hydronium ion concentration. So you want to be sure to check that. Now, if these concentrations certainly are not the same, and you'll get you'll have to solve for this right here. It's the same equation. If this was, say, 10 to the minus 1, and this one was 10 to, I don't know. They're different. If they're different, then you use the same equation to solve for hydrogen, and then get your pH that way. But for a 50-50 buffer, it's really easy. They're equal to Ka, and so the pH of a 50-50 buffer is minus log of the hydronium ion concentration, or the Ka value, which is minus log of 1.8 times 10 to the minus 5. I'll drop to 1.8, may go here. And so that would be a pH of 5 is what you'd start with in that. Now, that's one issue, calculating the pH of a buffer given the concentration before you throw in any excess hydroxides or excess acids. Okay, another problem is, well, what happens if you adding extra acid or extra base? And you're going to be asked, well, what's the new pH? Well, the pH of the 50-50 was 5. Well, we're going to throw in some acid. What do you expect the pH to do? For acids, it will push that pH down. Please check mark that. So you can kind of, some problems will look kind of complicated, but all in all, it just says, okay, what happens? And it'll add, the only one down there will be a pH in the acid range. Only answer choice. So, these are little wiry ideas. Okay, so let's add to our 50-50 buffer 0.01 molar extra HCl. So that's extra 0.01 and hydronium ion concentration. So the chemistry has to take that hydrogen out. Okay, so if we look at the equilibrium, right here, you've got an excess hydrogen that's coming in. So in this case, I would look at it in terms of the sea salt principle that we used earlier. So if you add extra hydronium ions, it's going to get heavier on the right side, and so that's going to cause your sea salt to tilt like this. And this is not at equilibrium. This is unbalanced. and this causes a shift in the equilibrium. So if it's low on the right side, that means you've got an excess of hydrogen plus OAC minus and HOAC. So that would cause it to shift to the left to reestablish a new equilibrium. With new HOAC, new hydrogens, and new OAC. Now in this one, as it shifts to the left, it'll keep shifting to the left to get rid of the hydrogen. Well, that means the OAC is going down and the OAC is going up in the shifting process. All right, now why did I do this? Okay, I'm giving you the chemistry and trying to get you, when you have to problem on there that says, okay, 0.01 molar acid was added to this buffer, calculate the new pH. What's the pH after adding? And so forth. Well, here's the chemistry. That chemistry has to take out the acid or base or whatever. So when you set this up, you want to set it up always, a buffer problem, around the equilibrium of the weak electrolyte or the weak acid or the weak base, like this. Okay, initially you had a 0.10 molar and 0.10 molar. Now you have an X concentration 10 to the minus 5 mole per liter. Then you dump in 0.01. That's kind of as if this didn't even exist to begin with. So what we do is just assume that that's zero before you throw in the acid or the extra base. Everybody got that? Because when you throw in that extra acid or extra base, it's going to be so much larger than what the equilibrium of your buffer would be that is negligible, and so you can make it zero. Okay? Okay, so what's going to happen? Well, it's going to shift to the left, so this is going to have to go up by 0.01 molar, and this one's going to have to go down by 0.01 molar because we've got too much over here. And so we want to get rid of all the excess hydrogen and return to an equilibrium of hydrogen, new hydrogen. So this has to go down by the amount of hydrogen, excess mess you put in there. So this would go up by the same token. And so at equilibrium, you get a new hydronium ion concentration, and this would be 0.09 molar, 0.11 molar, and that's your new equilibrium concentrations. And so your Ka is figured, and you solve for H plus, and you get Ka times HOAC over the new salt concentration. And so your new hydronium ion concentration is 10 to the minus 5, 0.11 over 0.09. So we have a new concentration of hydronium ions, so we can now calculate the pH minus log of 1.2 times 10 to the minus 5. Okay, so that's your new pH. We started at pH 5, so it went down 0.1. So it doesn't change much. Don't expect a large change. And so this is the entire process of solving our buffer problems that I have on the exam. Okay. Now, if you're throwing in hydroxides, I better say something about that. Let's look at this. Okay, adding excess hydroxides. Okay. Again, the chemistry has to remove the excess in here. And some hydroxide in here. This hydroxide is going to combine with the hydrogen. And so we will have a little bond right there. And this will take out that hydrogen in an amount that would convert all of the OH to water. And as a result, this is kind of like saying that the equilibrium now didn't have any hydrogen right there. Minus. And so the question is, how does it tilt? Well, obviously, this would cause the tilt to the left to reestablish the new equilibrium, to put extra hydrogens back in. And so as the shift takes place, this goes down in concentration, this one goes up in concentration, and it establishes the new equilibrium. So for HOAC equilibrium H plus plus OAC, and C initial, say 0.10 molar, 0.10 molar, we start out at 0. This time it's going to shift to the right here, and so we have to go down by 0.01 molar if we say we're putting in 0. excess OH, something like that. That's basically what you'll have to deal with. I just have different numbers. Okay, and this will go up by 0.01 molar, and so this side over here is 0.9 now. This one's 0.11 molar, and so you get your new hydronium ion concentration. So for your hydronium ion concentration from the Ka, your new concentration of hydronium ion. So now your pH in this case is minus log of the new hydronium ion concentration, which gives you a 5.09. Yep, 5.09. So we started at 5, so when you added base, it shifts up a little bit, a 5.1 if you will. And if you add an acid, it'll shift down a little. And I've given you the complete cross-section of what you'll see on the exam. Any questions about that? Okay, so we're adding an acid and a base together. Now this could easily be a weak acid over there. Now since this is a strong titration or mix, okay, everything's 100% ionized, so you don't have to worry about hydrolysis in this one. So what should we do? First, write your equation. And that's what you're going to be working with. Balanced is a 1-to-1 reaction ratio, right? And so we got 20 milliliters of 0.10 molar acid reacting with 30 milliliters of 0.07 molar sodium hydroxide. And so this is equal to 0.02 times 0.10 mole of HCl reacting now with 0.03 times 0.07 mole of sodium hydroxide. And so this is 0.002 mole of HCl and 0.0021 mole of the sodium hydroxide. Well, since it's a 1-to-1 reaction, it looks like this is the limiting reagent right here. It goes away first, and we'll have an excess on the base side. Everybody see that? Everybody good? All right. So what we want to do is to get the excess base, which equals the excess hydroxide, because this is a strong base, is 0.0021 minus 0.0020. and mole. And so that's a 0.0001 mole OH excess on the end down there. Well, that's moles. That's not molarity. So in order to do a pH calculation or of that nature, the concentration of hydroxide is moles over volume expressed in liters, molarity. So the moles is 10 to the minus 4 molar over, I don't know, 30, 20, 50 mils, 0.05 liter. And so that'll give you molar in hydroxides. Now I jumped over this pretty quick right here. So be sure you check mark that. Because when you get your concentration over here, who's the excess, you have to convert it to molarity, which is whatever you get moles divided by the sum of the two expressed in liters. That was 50 mils divided by 1,000 gives you 0.05 liters. Okay, and so I have a 2 times 10 to the minus 3 molar in hydroxides right here, and so the pOH is equal to minus log of 2 times 10 to the minus 3, and I get a 2.7 pOH. Okay, now the pH now is equal to 14 minus pOH, which is 14 minus 2.7, which is equal okay, so there's the entire package for working with a solution type reaction. Okay, now if you see, here's one that uses the weak acid and say a strong base titration, and you are to figure the ultimate okay, 0.1 molar HOAC, make it look like an HOAC, reacts with 25 milliliters of 0.10 molar NaOH. So this would give you 0.025 times 0.10 mole HOAC plus 0.025 times 0.10 mole of sodium hydroxide. Molarity times volume expressed in liters is moles. So that's 0.0025 mole HOAC plus 0.0025 mole NaOH. Well, obviously, in the reaction, HOAC plus NaOH goes to NaOHC, salt, plus H2O. So from this calculation, we got 0.0025 mole of the acid and 0.0025 mole of the base. And so if that's a 1-to-1 reaction ratio, then you're going to get 0.0025 mole of the sodium acetate. Now that will be in 50 mils of water, 50 mils of solution, which you'd have to convert to a molarity. Okay, so OAC concentration is now 0.0025 mole over 0.05 liters, and so that gives you molarity. And so that's a 0.05 molar in OAC. So that OAC now is a very strong, pretty strong conjugate base, which will in fact react with water. It'll pull off the hydrogen and form acetic acid and leave an excess of hydroxide. So we will work from the reaction of 0.05 molar salt and water. So here our hydrolysis reaction would be this. so initially, we're starting with a 0.05 molar in the acetate ion and 0 and 0 change in concentration. It'd be minus X plus X plus X, disregard the water, and 0.05 minus X, which is 0.05 molar, and that'd be X and X. Okay, now of course I'll give you the Ka value. So this is a Kb prime problem, which is Kw over the Ka of the weak acid involved in the hydrolysis right here. Okay, and so that is acetic acid formed, OH formed, divided by the salt. Okay, and so this works out to be X squared over 0.05, which is 10 to the minus 14 over, I'll just make it 10 to the minus 5, make it easy, instead of 1.8, 10 to the minus 5. Okay, and we solve for X, which is the square root of 5 times 10 to the minus 2 times 10 to the minus 14 divided by 10 to the minus 5. Take all of that moles per liter. Of course, that would also be the OH concentration. And so 15, 16, 11, the square root of 5 to the minus 11 looks like. I'll check on this. I got 7.07 times 10 to the minus 6 molar in OH. You double check that for me, somebody, please. Is it good?
Yeah.
Okay. All right. And so you're asked to get the pH, or the POH. If they wanted you to get the POH, just take the logarithm of it. Okay, so we'll go POH is minus log of the 7.07 times 10 to the minus 6. I get 5.15. And certainly the pH now is 14 minus 5.15, 8.85, yeah. So that kind of goes through a problem which starts as a neutralization and presents itself as a titration and asks you what's the equivalence point pH. So we'll start here, and then it shows how we work it relative to the moles. I convert to moles and then apply it to the equation. Of course, it's neutralization, equal volumes, equal molar. We got this, and don't forget to divide that by the total volume, and that gives us a salt concentration. Then we apply the hydrolysis problem right here. I'll get it all back on here. And in hydrolysis, you're going to always, whatever the salt is, if I give you one with the cation that here, it would still react with water, and cation pull off the OH, and you'd have an H excess over here. Everybody okay on that? If I had a cation right here, it would pull off the OH, and you'd have an excess H, but everything else is calculated the same way. So please make up your own, okay? If you have a salt, ammonium chloride, okay, well, ammonium would react with water. And give you the NH4OH. That's terrible. Okay. Give you NH4OH plus an excess of hydrogen. And you'd apply it to that, and you'd come out with an ask your pH. You wouldn't have to do both of these steps. Now, I'm just drawing a typical titration curve, adding a base into an acid. Now, when you look at the curve, how do you know it's a base into an acid? Well, you're monitoring what's in the container. And so the base is up here, adding into an acid down here, and you have your pH electrode and the one at the bottom. Now you can switch these, and if you had a base down here and an acid at the top, it would come from the top up here and go along and down and so forth. But what I'm about to show you is the same for both of the issues. Now, where's the equivalence point? Well, it's right in the middle of the inflection, right here. And it doesn't matter whether it's strong, 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 weak, or weak, strong, or whatever. You're going to have a curve that looks like this, and right in the middle of the inflection is always the neutralization or equivalence point. So, there's your equivalence point. Let me draw us a little reference line right through here. Now, this is an acid, a base into an acid, sorry. Okay. As you add the base in the beginning stages of the titration, what's the limiting reagent? What's the limiting? You missed that on that quiz. I remember you asking me about that. It's the base. It goes away first. Okay, everybody got that? Okay, the limiting reagent. So this region down here is a limiting reagent. And in this case, the base. Now, if we turned it over, and I gave you one that started high and went low, the acid that you would be adding would be the limiting reagent in that case. So, don't trust me. In other words, I may give you one that's backwards. Anyway, so the limiting reagent's the base. See how the pH here retains its dominance? That means while you're adding base, the acid is always in excess. So in this region, acid is in excess until equivalence point. Hope you can read that. Until you get to the equivalence point. How much original acid and base do you have at the equivalence point? Remember that problem I gave you on the quiz way back when? Zilch. 0. Everybody okay on that? Because when you have equal amounts of acid and base react together, all you've got is salt left. Everybody okay? Acid plus base gives salt. And so at equivalence point, only salt. And so when you get to the salt point, you either got hydrolysis or not. If it's a strong, strong acid and base, the salt will not hydrolyze, and so the pH right there would be what? 7. Everybody okay? So that's a strong, strong. But if you have a weak, strong, okay, a weak acid, strong base, it's going to push up the pH higher because it's going to have an excess OH because the base is hydrolyzing. OH. Base is hydrolyzing, the conjugate base is hydrolyzing, what I want to say, and it's leaving you in excess of OH, so this is going to shift up. If you have a cation reacting with water, it's going to push the pH down, okay, a little bit, and you have to work out an hydrolysis problem at that point. Now, above this, what kind of reaction are we having above the equivalence point? What is the reaction? Listen to me carefully. What is the reaction above the equivalence point? Let me ask it a different way. Is there a reaction above the equivalence point? No. Okay? Because that's where you have an excess. So you've already neutralized all the acid down here. So you don't have any acid anymore down here. So any additional base, it just lays there and makes base pH. See the point? Everybody good? Okay. Because I have little sneaky questions like that. What's the reaction above? No reactions occurring above the equivalence point or past the equivalence point or something like that. So base only in excess. No reactions are taking place, and the base only contributes to additional increasing in pH. So it just keeps going up until it levels off and
it'll stay it'll stay under 14. Yeah, what's your range of acids and base pHs? Anybody know? 1, 2, 14. So be sure to keep that in the back of your mind, because I like to throw that one out. I sent y'all an email that had a real weird looking, if anybody saw it. It had the pH line on it. Did you see that thing? It's a neat little graph. Shows you all the different stuff that has different pHs and stuff. Okay, well, be aware of not just where the equivalence point is, but also some of the chemistry that goes on around that curve and what you can derive from it. Where would you have to go in this curve to get Ka value for a weak acid? Where in this curve would you have weak acid?
Below.
Halfway point, right? It's halfway between the equivalence point and that. Why is that important? Because the acid remaining equals a salt concentration that's in the solution too. So you have at halfway point, you have no salt here. Over here, now watch this, on the starting, you have all acid, right? 100% acid. Over here, you have 0 acid, all salt. Halfway is kind of split in the middle. So your acid equals your, well, I've got an HOAC on the mind, your acid equals your salt right here. So once you get that, then you get the say the pH at that point. Well, the pH at that point equals pKa. And then you get your Ka by taking the analog of it. So at this equivalence point, right here where salt and acid are equal, if you have an acid, let's take HOAC, okay, goes to H plus OAC. And at VEQ over 2, say if you're titrating a 0.1 solution, you'd have 0.10 molar here and 0.10 molar there. And so at that particular point, your acid equals the pH over there, and there's also the pKa. All right, HOAC, Ka equals H times OAC over HOAC. And if these are equal, that cancels out, gives you your hydrogen. Well, that means that pKa is equal to pH at VEQ over 2. And you can get the, and it doesn't matter, you can use any weak acid and do this and titrate it with a strong base or something and find out where that equivalence point is. Take the halfway point, and it's the pKa, take the analog, and 10 to the minus pH or 10 to the minus analog. If you've got given pH, H concentration is 10 to the minus pH. Please write that down and practice and note that, because I do give those kind. What's the pH of a such and such and such your hydrogen concentration? Something like that. And so 10 to the minus pH gives you the hydrogen concentration. And real quick, if you get a pH of 2.6 or something like that, well, it's 10 to the minus 2.6, and that gives you your hydrogen concentrations. So be sure to check that. In solubility product equilibrium, there's some specific kinds of problems that you'll have to work, and I give one of each. You can count on it. So let's itemize those to begin with, okay? Calculate solubility from KSP. Remember the X value equations. That's all that is. The X in square root, if it's a 1 to 1, 1 to 2 is KSP over 4 square cube root, those kind of things, okay? Now you'll have to calculate KSP from solubility. They're giving you some solubility value. Now, in this case, to calculate, you have to do two things. You have to convert your solubilities, okay, to ion concentrations. If I gave you a lead iodide and KS, okay, so you're given the solubility out here. What's the KSP of the salt? So in order to work work this one, you have to be able to write the KSP expression.
So this would ionize to 1 part lead and 2 parts iodide. Well, the solubility happens to be the lead concentration, but it is not the iodide concentration that you would have to use. How do you get the iodide concentration based on this? It would be 2x. Okay, so PBI2 would deliver ions in this capacity, X and 2X, and X is this in moles per liter.
Okay, so to get your iodide, you would have to double that.
And then put it in the KSP expression, lead and I2. Don't put if you put 2x in there,
But that's not 2I. So that'd be mean 2 times 2. That's wrong.
okay, so like that, and so that one would go there, and that one would go there, whatever they are, and and there's your X, and you put it in, substitute your numbers,
You got it. It has 2 parts to it. These are pH effects in salt solutions.
One, if I give you a iron hydroxide and with a KSP value or something like that, calculate the pH of saturated
Solution. Okay? So saturated solution would be whatever the amount of hydroxides would be delivered, and that saturated solution, then you take the POH and then subtract that from 14, right? Everybody good?
Oh, hope so.
8 times 10 to the minus 16.
Well, when you calculate
The solubility of this, it will be the amount of iron delivered,
but it will not be the amount of OH. So this is a cube root of 8 times 10 to the minus 16 over 4, and that'll be your solubility, but it'll only be the iron. You have to go 2x to get the hydroxide concentration,
and then go calculate.
the pH and stuff like that. Okay, so working this out, I get 5.8 times 10 to the minus 6 as a solubility using the cube root formula because it's a 1 to 2 ionization. Well, that represents also the iron because this is a 1 to 2 ionization since you have 2 parts hydroxide for every 1 FeOH2 delivering ions, then you have to double that, and so here's your OH, and then you can get your POH, taking a logarithm, 4.93, and then 14 minus, put it under here, and pH is 14 minus 4.93, 906.07. Yeah, 07.
So that's one type of problem. Here's one. It'll take me a minute to put it together. I'll let you copy on this thing for. Okay, lime scale is a salt, calcium sulfite. Okay, and you have other kind of lime scales or salt scales, magnesium sulfate, sulfites, iron, all kinds of things. But I just chose this one, the calcium sulfite. How could you increase the solubility of this? Now, the reason I'm asking this, if you have a Mr. Coffee or something like that, and over time the heating element in that thing will coat up and with salt lime like this, and it'll ruin it. Okay, but there's something you can do to get rid of that, and you can add what? An acid. You can add a weak acid to it, and it'll solubilize that lime, and it'll get rid of it. Also, inside of washing machines, sometimes you see a white coating. You can take some vinegar and wipe off the inside of it, and it'll solubilize it. Now, why does it solubilize? That's the concept here. When you look at calcium sulfite, it ionizes 100% to calcium ions plus SO3 minus 2 ions.
okay? If you put an acid into a solution, the acid will react with the sulfite ion because the sulfite has a strong attraction in -2 to the hydronium ion or the hydrogen, and it'll make a bisulfite ion, which is a weak acid, and this is soluble. Now, one of the concepts I want you to get in your mind is what's happening in this process of putting the acid in with the calcium sulfite, because this has almost zilch solubility, you know, I mean, it's really low, and so you have a calcium sulfite in water, it's going to precipitate. It takes very little concentration to precipitate. So, but when you put this acid in, it's like the excess OH and excess hydrogen. If you put excess OH into a weak acid buffer, then the H will combine with the OH. Well, H combines with the sulfite here. Calcium sulfite, calcium +2 plus SO3 2 minus, and if you put the H in right there, this will combine right here into a hydrogen sulfite, which solubilizes. The HSO3 will go into solution. Okay, so put this way, HSO3 minus, and that's in solution right there. So you've gotten rid of it. So what happens is you've got this issue. You've created a void right there. Let me move that down a little bit so I don't crowd everything. So you've taken the hydrogen and put it in, and it takes out the sulfite. Let me put the calcium back in there in the right place, if I would. Plus, now, you don't have any sulfite in there anymore. So what happens is this ionizes to deliver more sulfite and more calcium. Well, calcium's soluble. Okay, and if you got extra H's in there, anything else you throw in there, the sulfite will keep ionizing. Calcium sulfite will keep delivering SO3s into solution until all of this is gone. Okay, and then you solubilized all of it. You keep putting enough acid in, and so it will keep going to this until all of the acid, salt is dissolved. Okay, so you'll find one of those. Which of the following procedures would increase the solubility of a salt? Okay, and increasing the, adding more acid or decreasing the pH or something of that nature in the answer choices. So, okay, you'll have problems where concentrations will be given ions that will be mixed together. And for a salt, A, B that goes to A plus B minus, then the KSP, say, is A concentration times B concentration if you're at saturation. However, if the A and B concentrations are such that they are not at saturation or not here, what you'd calculate is a QSP value. These are not KSP values. Okay, and what you do is you compare the K and the Q, and defining which way the system would shift, it defines whether or not a precipitate will be formed. Now this is a solid over here. Okay, so if you have a KSP that will shift to the right compared to the Q, okay, and when you show a shift to the right, that means no precipitant is formed. You see how the arrow is pointing to the ion side? If you shift toward the ion side, you get no precipitation. However, if you work your problem out and the QK comparison tells you you're shifting to the solid side, then yes, precipitation forms. So how do you tell? Okay, if you recall, I said K comes before Q in the alphabet, so put it down 3 times. and then QSP 3 times, and then inequalities on the ends and one in the middle. If you have KSP equal QSP, this is a saturation. Any further addition of salt will precipitate. That's another question. Do you see precipitation at saturation? That's correct, no. You do not see precipitation. You just got a lot of salt. You got all you can put into the solution. You're at maximum. You put one more molecule of salt in, and then it starts, that one will not dissolve. It'll just fall to the bottom and stay there. So, now, if you set this up, as I've shown you, the inequality points in the direction of the shift based on what you've written up here. Okay? If you have the solid before the ions, and you set it up like this, the shift will be toward the solids, and you can make that an arrow. Or in this case, where KSP is greater than QSP, then the shift is to the ion side. Okay, so it's always solid to the ion. Now you'll see them turned around, basic, but this deals with the solid to ion order, if you will. Everybody got it? Now all you have to do is, see, the problem will give you the ion concentration. You multiply them together and they'll give you a KSP number, and you just compare big number, little numbers, or equal, and determine whether it's going to go in solution. That's all you got to do. Okay. Okay, common ion effect functions to do what? Reduce the extent of reaction, right. So in this case, it reduces the solubility. Okay? Now when we're talking about acids and bases, it just reduces the amount delivered in solution, which could affect the pH. Everybody okay on that? Okay, so the common ion effect occurs in both the acid base and the salt issue. But you have to be conscious of the effect. The effect in acids and bases is just, it doesn't deliver the ions, okay? And will shift the pH a little bit. In the salt thing, it just affects the solubility. So you'll have less material going into solution, okay? All right, so functions again, I'll put that down. Extent of reaction, I'm just going to put solubility. Of the salt. So if we're given silver chloride as an example, getting tired, Cl minus, and KSP is, I'm going to 1 times 10 to the minus 5. Now, again, so it's going to be confusing. I'm doing this to simplify the math in the thing. The KSP for silver chloride is 1.8 times 10 to the minus 5. So now, to work this and understand this, you need to compare it with the pure water solubility. So in pure water, solubility is simply the square root of KSP, which is square root of 10 to the minus 5, excuse me. 10 to the minus 5, and let me get that one. 10 to the minus 5 square. 3.2 times 10 to the minus 3. Okay, so we'll have 3.2 times 10 to the minus 3 mole of silver chloride delivering ions into solution. Anything over 3 times 10 to the minus 3 ain't doing nothing. It's just laying there, inside. Okay. Now, AgCl in presence of 0.01 molar HCl. Okay. Calculate the solubility like that. So this is essentially the same setup, except you can't use the X formula. Minus. So in HCl, that's 100% ionized, it's O1. This will represent the new solubility. Now, You disregard that, and we'll just say that's the equilibrium issue. So KSP is equal to silver times the chloride concentration. That's 10 to the minus 5. Ooh, come on, JP. I am sorry. I'm brainless. I'm thinking acids. That's 10 to the minus 10. Somebody get on my case, will you? Then this comes out 10 to the minus 5. Ooh, sorry about that. Okay. Having acid numbers on the brain here. Okay, that's 10 to the minus 10 here. So we got 10 to the minus 10 is equal to x to 10 to the minus 2, like that. And so our solubility now is 10 to the minus 10 over 10 to the minus 2, which is 10 to the minus 8 molar. So there's your solubility with the common ion, and there's your solubility with the pure water. Okay? Now that shows a drop. And that's about the long and the short of what I'm going to show you on common ions. I mean, it's either going to knock it down or not. Okay, last topic. Okay, complex ion equilibrium. I just worked through one. Complex ion equilibrium functions to increase salt solubility. How? By forming complex structures that are soluble. And just like the buffer action, where it started taking items into the solution like OHs and excess and combining with hydrogen and creates a void in the equilibrium and shifts the reaction. Well, that's what the complex ion does. If we have, say, silver ions in the presence of ammonia, this will react very quickly to form a silver amine complex, and this is primarily the one I use because it's easy. It's a one that it has a small K formation. Not to worry. This has a KF, something like 1.7 times 10 to the 7th. Very strong formation of that. So anytime you put ammonia in the presence of an ion, there are other compounds that can be formed, complexes like this. This is the one you'll see on test day, and it gets the principle across. Okay, so what's the solubility of silver chloride in the presence of, say, a 0.1 molar ammonia solution? So and I'll have to give you the KSP numbers and the KF numbers, which are 10, well, I'll have to write this one out, 1.7 times 10 to the 7th, like that. So that's your problem right here. And so you've got to calculate a new solubility with it. Okay, well, the solution, AgCl, sets up to Ag plus plus Cl minus. Now that's what the normal ionization would do, but what you're going to do is you're going to throw in an ammonia. Well, you have to show a reaction of silver with the ammonia, whatever is used. And this forms a silver amine complex right there. So you have two reactions that you have to put together on this. Well, what does that mean? You have a net, and you will add these two together. Okay? When you do, you see that the silver is on the opposite sides of the equilibrium symbols, so you can cancel those out. And then you'd write everything else down here. Okay, so there is your net reaction of the two. Now each one has a K value. This is KSP is 1 times 10 to the minus 10, and this is K formation, 1.7 times 10 to the plus 7. You don't have to put the plus in there if you don't want. So, like that. So when you have the net reaction, when you add two reactions together to get the K value for the net reaction, you multiply the individual K values together. So the K net is KSP times K formation, which is 1 times 10 to the minus 10 and 1.7 times 10 to the plus 7. Keep going, right, minus 7. Right there. And so that's 1.7 times 7, 8, and 10 minus 3. Okay? So that 10 to the minus 3 says we're going to get a little, it's a lot larger than 10 to the minus 10, and it's quite high. So we're going to have to apply squares and so forth. I'll show you. Okay, take the net reaction. Let me rewrite that. And this is the net reaction is what you want to build your equilibrium out of. Okay, so initially, always disregard the salt in itself. It's infinitely larger than all the rest of the substances in there. But you can't ignore the ammonia. So we have a 0.10 molar ammonia solution. And when this comes together, you get X and X. And then so let's just make it equilibrium. Okay. Here. So you build your equilibrium expression. Your K net is silver amine complex times chloride, all divided by, move that down here, ammonia. And you got to square that because there's two of them. Okay? So now the K net is KSP times K formation. So substituting these into your equilibrium expression, you wind up with X squared over 0.10 squared. Oops. Not. I forgot to put the minus 2x in here. God, sorry about that. The point is, I can't drop the 2x. That's what I immediately saw that. Okay, so you have to use that value of whatever the concentration of ammonia is minus 2x, and you can't drop the 2x. And you want to check mark that. And so when you put it into the 0.1 minus 2x and square that, okay, you either have a quadratic to deal with, or you can get rid of the squares. That's why I don't go to cubes and stuff like that, because we don't have time to go through polynomial solutions. So KSP times KF, that's 1 times 10 to the minus 10 times 1.7. Well, I already did it, didn't I? Yeah, 10 to the minus 7. Put that down. 1.7 times 10 to the minus 3. Okay, we're closing in on it. So X will represent the solubility of the silver chloride in presence of the ammonia. So what we need to do to get that, we take the square root of both sides of this. Got that, okay? And so this gives us X over 0.1 minus 2X to equal 0.0017. So now we're in a position to solve for X, and X represents the solubility now. So a little algebra going on here. And so that's 0.0017, and times 0.1, we had another 0 in there. 2 times 7 is 14, 2, 3, 0, 0, X, zeros in. And it's right there. Okay, so we have a 1.0034X is equal to 0.00017. So X is now 0.00017 over 1.0034. That'll be in molarities. So I get 1.6 and 10 to the minus 4 molar. Well, in fresh water, the solubility was 10 to the minus 5. In common ion, what did we get in common ion? 10 to the minus 8, was it? Something like that. Remember? Yeah. So the issue in here is you want to be able to compare either the common ion to normal solubility or the complex ion solubility in to the pure water solubility.